Thank you, Doug. I'm not really sure why you're all here. Maybe you're early for the ever-popular Sam Savage, who's in this room a little later. But one of the reasons I'm here is that as I was driving to the airport in Green Bay Saturday morning, there was 2 inches of snow on the ground. So that was my motivation. So I guess they're taping this, which puts a little more pressure on me, but it takes some pressure off you. You can take a nap after lunch and still catch it on the Late Show, I guess. Just one other comment about questions. So you can ask questions during the talk. There is a criteria, though. The question should be either the question should be more interesting than what I'm saying, or your expectation of the answer being more interesting than what I'm currently saying is kind of the criteria to follow. But if you can meet that, jump in with a question. So I'm with Schneider, and what I'm going to do is talk. I got 3 parts to this talk: a quick overview of parts of the company to give you a perspective on who we are and what we do, and then I want to talk a little bit about an integrated approach to analytics across a couple of different areas of activity. And then after I go through that and talk about some of the challenges and important components of that, I've got a couple of case studies that I want to go through and show the relationship between these, what I call components of analytics. So to start with, Schneider has 3 main divisions represented by these 3 parts of this picture. So on the left is truckload, which are full containers that move from a truck from point A to point B. The middle represents our logistics operations, so traditional 3PL logistics and brokerage and supply chain management. And then on the right is intermodal operations, which I will talk about in a little bit more detail, but this is truck to rail, back to truck. So just briefly, we were founded in 1935 when Al Schneider sold his car and bought a truck, and have grown since then. You can see some of the numbers about the company. The relevant ones for my discussion are we've got between company truck drivers and owner-operators, we're at about 13,000 tractors, which is actually down from pre-recession. We were up around 15 or 16,000 at a time. And then down near the bottom, we've got about 45,000 trailers or containers. So a lot of our operations involve dropping a trailer, picking up another trailer. The efficiency of the network is improved if we're able to get trailers preloaded and then drop them loaded and take that time out of the system. So those are probably the 2 components of these numbers that are most relevant. So when I'm referring to integrated analytics, I'm thinking of a process that has 3 corners on a triangle: exploration, discovery, insight, kind of general analytics that you think about doing, just looking at data and trying to uncover patterns or figure out how it is relevant to your business processes. Operational decision support, where we actually have analytical engines that do either forecasting or optimization, and they're connected or embedded in some way with operational processes. And then the third part is business intelligence, which is dashboards and reporting that monitor and sense activity related to those integrated decision support tools. And then I'm going to talk a little bit about how these things kind of feed each other. So exploration and discovery, I think there are 3 simple questions. Should we do something? What should we do? And how should we do it? And you might think, should we do something is obvious. Of course we should do something. We work here and we do this kind of work, and that's what we're paid to do, so we better think of something to do. But certainly in our organization, there have been a number of things that have been done and have cost a considerable amount of money and IT investment, that when we did the analytics after the implementation, we realized it was something we shouldn't even have done. Either because it didn't really make sense when we thought about the business process correctly, or the data wasn't there. I mean, you probably all have examples of building something out based on some variable, and when you get to the end of it, you go back and look and you say, well, that variable is a uniform distribution over the lowest possible value to the highest possible value, and I'm trying to do something intelligent with what the values are that I'm seeing. So that's the kind of thing I'm talking about. So there are three components to kind of figuring out whether or not we should do something in a certain area. The first is the data. Do we have data, or can we get data? Is the data that we either have and can get, is it good data, or can I make it good data? So those are things that an analyst needs to work through and think about before embarking on a project. Probably the one that gets missed the most often is because this isn't necessarily the technical part. I mean, we can go solve the technical problem without asking the question, are we really willing to do what's necessary in terms of the processes in the business to change the processes to effectively utilize what it is that we're intending to build? And then the third is an obvious one, the return on investment. So if I think about the next step, okay, once I've decided to do something, I've done some preliminary analysis, the what and the how, looking at alternatives. So I may have a simulation type alternative versus an optimization type alternative versus an alternative that doesn't involve technology at all. So that's kind of the first step. And then what does the data support me being able to do? So again, very data driven. Let's not build a model that seems elegant and sophisticated and looks like it's a match for what the business needs, and then find out later that the data either the data that's available or the data that we can make sense of doesn't support the return on investment that project would generate. And then statistical analysis of this data is really just kind of a follow-on to the second point. The fourth point here, again, back to the implications of the business impact and change, implications both in terms of the softer sides of things, you know, how are people going to adapt to whatever the new technology is. We certainly have, one of the ones I'll talk about here is a decision support engine, which is pretty sophisticated, it does optimization, and I'm sure a lot of you in the room have had a situation where you've had something like that, and getting the users to accept it, even after you've gotten the executives to accept it, is a challenge that you should really think through in the beginning. And then certainly refining the cost estimates for both the business impact, development costs, as well as the benefits there. So that's a little bit about that. Now when I talk about an operational decision support tool, I'm thinking in terms of 3 or 4 key components of implementing something. So if I'm thinking about embedding some intelligence in a system, I've got to think about how that embedded intelligence, that module or component, is going to work with whatever the surrounding ecosystem, the user experience, other transactional processing, how those are going to fit together. Now in our case, we have a couple of examples where we have commercial software from a well-known vendor that we've installed and configured. Certainly it has some structural limitations, and then we've built some intelligence outside of it. But then the connection back in, both in terms of processing time and the ability for the commercial product to capture the intelligence. I mean, you can be as smart as you want, but if you have to communicate through somebody who's not quite as smart to a third party, there's a certain amount of loss in that communication process. And I just thought of that analogy, which is probably a pretty good one for some of our systems. But and then the impact on performance. So in our case, we built an interesting structure that is kind of a data hub that gets data from the real-time system and serves that data to these other modules that perform intelligently, and it only needs to be about within 5 minutes in terms of near real time. So we're able to make some trade-offs in that component in order to lessen the impact on performance. And then I'll talk about both prescriptive and predictive models. So in terms of either forecasting or predicting what certain variables or values are going to be in the near future, and then prescriptive in the sense of then suggesting back to the solution process what the right approach should be. A key component of building an operational decision support tool is thinking of how you want it to interact with the user. Kind of the lightest weight approach is a decision support tool that gives guidance. So, kind of a suggestion, headed in this way, stop taking orders about 2 o'clock, something that's a little bit softer, and then in between is something that makes a firm recommendation, but for various reasons you've decided you're not going to force compliance, either because there are qualitative factors that you'll never be able to include in the model that you want the user to be able to bring into the situation. That's certainly the most common example. And then the strongest is, here's the answer, make it happen, or in some cases we're going to the point where it's not, here's the answer, make it happen, it's here's the answer, send it right out to the, whatever the component of the system that actually performs the execution is. So that, those are important. And then other issues to deal with, I think in these kinds of things, prototyping and iterative development are extremely important. And I won't go into the details of selecting the tools to do that, but that's certainly an important component of thinking about building something that you're going to want to do prototyping and iterative development and end up with something that is going to be robust and industrial strength. So, do I just build it in Java or C++ to start with, or do I use a modeling language or a prototyping environment that's more efficient at that stage and then pay the cost of re-implementing? I think more and more there are some capabilities in the market that allow you to kind of bridge that gap and gain a lot in the prototyping space and give back not very much in the final solution robustness and performance. When I talk about business intelligence, it's usually in the space of dashboards, portals, and reports, and I'll have some examples in my specific context to talk about those. In that area, I think it's one of the things we've learned is it's worth the upfront investment in putting together a platform that's robust and efficient and flexible so that I can build these lighter weight components as quickly and efficiently as possible, and then also prototype in that context. The fourth bullet is really one that we've struggled with over and over again, and that is a lot of times the business will say, I need a report that has this stuff on it. And you lay it out and then they don't use it. Or it turns out this report has no logical place in the business process that's being executed. And then those reports just disappear. I mean, when we went to a new system, I can't remember what the number was, but it was a number that was beyond belief. 50,000 reports, 100,000 reports that had been, most of which were still generated because nobody told IT they didn't need them anymore. So that, I think that's a very important thing. When you design a system, you should be thinking all the way through the business analytics that feed back into it. I'll show you some examples of that. And then the last component, which is something that's relatively new, and we're just starting to go into this area, is So traditionally the BI group developed reports and dashboards, and the most sophisticated calculation they may have done was to compute the average of something, and usually when they did compute that average, it turned out the average was meaningless in the context of what they were trying to do. So the idea of having a BI group that can quickly build user-friendly dashboards that have been well designed and give you all these filtering and selection capabilities, but at the same time have the connection to an online sophisticated analytics package like R or SAS or certainly one of the others that's out there, SPSS, is certainly something that we're just starting to look at. So I don't think there's a lot of maturity in that area. I know some of the products, at least the ones we use, have just been released in the last year or two in terms of allowing an effective connection between this user-friendly, flexible environment and, and deep mathematics and analytics, data mining, optimization in the background. So if you're going to do this, if you're going to tie together these three things, you need, I think one of the most important things is to invest ahead of time in a data infrastructure that is as clean as possible, consistent. So one of the phrases you often hear is one version of the truth. So to try to get to that, it's got to be timely, and timely can mean both not too latent, but it can also mean not too quick. So you should be thinking about, I don't want to invest a lot of money in having this big data store replicate the operational systems every 3 seconds if I'm not going to get the payback from doing something like that. So kind of right-sizing that performance is an important component. And it's got to be accessible in various ways to various communities. In the case I'll show, our engineering group has a considerable amount of access into this data at a level that's appropriate to an engineer, whereas business users also have access into most of the same data at a level of complexity that's appropriate to what their jobs are. And then certainly this involves different teams and different skills, so the idea of putting together interdisciplinary teams to think through the analytics process, I think, is a key component. I know I've learned a lot in the last month sitting down with some of the people in the BI group, and I hope they've learned something as well. And then I'll talk a little bit about the tools, and then the process, which relates back to the team skills, is making sure that you've set things up so that this collaboration can really occur because the objectives among the group are shared. So if the engineer's objective is to look as smart as he can at the expense of anybody else on the team, that's not going to be effective. And if the business member goal is to emphasize the fact that knowledge of the business out-trumps anything else, you're not going to be effective in that case either. So I'm going to get a drink of water while you guys ponder this this slide. So this, I confess I was a little bit lazy. I got this from the BI group, and I probably could have abstracted and simplified it somewhat, but just to kind of summarize, so on the left-hand side, we've got kind of our operational, oh, I've got a pointer. Does that work for only Jack in the front row? Anyway, so over here we've kind of got our operational system. So up here is kind of the master data that's more or less static. So customer master files, product files, supplier files, various list of values and attributes that are, used to run things. And then down here we've got in this environment I'm talking about, we've got 6 kind of main areas of operational systems. The 3 on the left are the 3 commercial software products. This is all the financials. This is order entry and customer management, and this is the transportation management execution system. Then this is a maintenance system. We've got some key components that we have built to do revenue management and some other things that just are not very likely to be found in a commercial software product. And then we've got a host of other little bits and pieces, some of them from third-party vendors, so communication systems. There's some systems that deal with government compliance and a variety of things like that. And then we've got kind of our information delivery environment, which is a data warehouse, which basically feeds into a number of kind of self-service areas. And I know you can't read this in the back, but so there's an executive information system, financial reporting, scorecards, and things that give us business tempo, performance monitoring, and various operational reports. So one thing we've done is wherever it made sense to not need a real-time report, we've tried to move it into this environment rather than, even when some of these systems have the capability to develop reports and work right out of the data, it turns out that for performance reasons that's not a good idea. And then, so this operational data store was originally built for the engineering group so that we could go in and muck around. But it's kind of expanded to other uses, and this is a specific financial reporting system. And then we also have, I didn't draw it on here, but there's also another big piece down here that gets data out of here and feeds into some of these real-time decision support systems or near real-time decision support systems, and then feeds information back to it. So that's a little bit of kind of the picture of what this data information framework looks like. It was a considerable investment, both in the purchase of the software platform to do it, and there are a number of vendors out there that I think have products that are relatively equivalent. We don't have anything going on that I would really refer to as big data. We've got lots of data, but I guess we've got lots of little data or whatever it means not to have big data. But since we're a business-to-business organization, we just don't have that. In some of our telematic information, we're starting to approach some of that, but yesterday I learned how to use Hadoop, and I'm just chomping at the bit to figure out how I can, muck this up with some Hadoop. So, let's see. So how am I doing on? Where am I in my time frame?
25 minutes.
So I've used up about half. Okay, good. That's kind of where I hoped I'd be. So the first half of this talk was sort of I kind of put it together because when I was going to throw my name in the hat to give a talk at this conference, I thought integrated analytics, cool. That's right on what they'll like. And so that's the first half. The last half is really the cool stuff. So. But anyway, seriously, I've got a couple of examples I want to go through that hopefully will show you this flow from discovery, exploration, into building a real-time decision support tool, and then the BI monitoring that kind of comes along with it. So just to give the setting so the 2 examples I'm going to talk about are related to operational decision support. So this is in the space of daily operations, of getting freight from customers, figuring out what to do with it, and then doing it. So we move about 11,000 loads a day, and this is just in the full truckload space. So these are almost all either 53-foot trailers or 53-foot containers that are on a chassis when they're on the road and then are double stacked when they're on the railway. So our drivers drive about 8 million miles a day. It's a lot of miles. Intermodal, our containers move about 2.6 million miles a day. And then to kind of get an understanding of how stuff flows through the system, this is a couple of years old, but it hasn't changed much. So this is just a little bit of a histogram that kind of gives you a picture of how far in advance of needing to pick up a trailer or go load a trailer, we actually get the call from the customer and they tender us the freight. So I think the mean is somewhere around 2 days. Some of you that can do visual mathematics in your head can probably calculate the mean just from looking at the bars. As little as 2 hours, and then beyond 7 days, there's some that goes out as far as 2 weeks, but it's pretty minor. And then just to kind of give you the full picture of, so that's the work we got to do. This is the stuff we do with that. This is just kind of a quick, simple visual to give you kind of a picture in your mind of what's going on. So on a given day, each one of these lines represents an origin-destination pair that a truck would be moving along on that day. Now this has changed. I need to update this, but I can't remember how to make it draw, so I'll have to have Mike help me with that, I guess. Or Bob. Bob is the one that does that. But so now, actually, this same idea, there's a lot of stuff moving all over the place. The main difference is there's probably less going back and forth here and more going on the west. So we've moved more into the west, and we've replaced a lot of longer haul freight with intermodal. In fact, several years ago, if it was under 2,000 miles, it would probably go truckload. If it was longer, it would go intermodal. That number has come all the way down. I don't know, it's probably 700 or 800 now. I was talking to our intermodal operations vice president this morning, and he says that number will be down around 500 in a couple of years. So keep that picture in mind when we go to the next couple of slides. So I'm going to talk about two parts of operational decision making. The first is I get the call from the customer, or I get an EDI message from a customer, or I get an email from a customer, or I might have some recurring freight that I know is coming up, and I need to make a couple of decisions. Should I say yes or no? Sometimes I don't have a choice, but sometimes I do have a choice to say no if it doesn't look good to me. Most cases I already know exactly how it's going to move. Typically we know ahead of time whether it's truckload or intermodal, or if it's going to go to a regional fleet. There is some intermixing though, particularly in our main big fleet. There's a combination of drivers who drive by themselves and are subject to the strict drive for 11 hours, take a long break, and so on. So that limits the movement of that truck. We also have somewhere around 15% that move in with teams. So there's 2 drivers in the cab. So that truck can run 22 hours a day. One sleeps while the other one drives. Obviously that's a more expensive option, but depending on the freight and what the delivery requirements are and whether or not there's a suitable premium price, that can make sense. And then in some cases we'll be able to negotiate a price, and others we won't. And then hopefully we have some flexibility to agree on when the pickup is and when the delivery will be. And on the next couple of slides you'll see why that's important. Once that's done, I got the order. I've already agreed to move it. The price has been set. There's some constraints on when I have to pick it up and when I have to deliver it. And within those boundaries, I then need to figure out who to assign it to, how to source the trailer, how to deal with the trailer issue. And then I may have to go back and modify some solutions based on some balances in the network that you'll see on another slide or two. And then dispatch it, you know, give the instructions to the driver and the railroad and whatnot, and then pay attention to what's going on. In the first phase, my objective really is to maximize the estimated profit, because I'm having to estimate some things, the realization of which may or may not be what I estimated. So that's my main focus. And that profit also is a number that's includes some soft costs to help us do some things that aren't directly quantifiable. And then once that's happened, the price is already set. I want to do it at as low a cost as possible, meeting whatever service commitments or requirements that I have. So it's really a two-stage problem. So in the first example, I really expected there to be an interesting question by now. Maybe more of you took me up on the video nap option than I anticipated. So I'm going to give, in this flow here, I'm going to give a couple of quick examples of this analysis that occurs on the front end. I'm going to talk about a couple of decision support models. And then I'm just going to quickly show you what a user interface looks like for operations that sits in front of these decision support models, and then a couple of dashboards. So think back to that picture with all the lines going like that. In a 2-month period, we had, and this was, I pulled this from last fall, I think, we had 654,000 shipments, so about 1,000 a day. They came from 28,800 distinct customer locations, and they landed at 26,000 distinct customer locations. And of those locations, a little over 23,000 of them appeared both as an origin and as a destination. And then what I did was just a quick distribution here of by the number of shipments in the, so these numbers here, these are the number of shipments in different groups, and these numbers should add up to the number of locations, so somebody can check that. I hope I did. But what that says is 21,000 outbound locations only had one shipment in the 2 months. 18,800 inbound locations only had one shipment. And then there were only 13 outbound and 14 inbound locations that had over 1,000 shipments, and then the numbers in between. So the point is, it's pretty scattered. And the fundamental problem I'm going to talk about here has to do with the notion of when a truck makes a delivery and drops a trailer or empties the trailer, the next thing it's going to do is pick up a load, either pick up a loaded trailer or take a trailer and go load it up. It's got to go from where it dropped to where it picked up, however far that is. And we don't get paid for that. We don't get paid for the driver time, we don't get paid for the fuel, we don't get paid for the depreciation of the equipment. So we want to try to make that small. So the idea is, well, how do we get our heads around these big numbers? This is just the volume by day. You can see it drop on the weekend. I think I thought, I got a little space at the bottom of the slide, I should put a graph on it. Actually, it looks nice kind of from balance, but it doesn't really tell you much other than freight's fairly consistent day by day. It certainly drops way down on Sundays. Saturdays are low.
I have a question.
Yes?
There's relatively static backs to that. Is that driven by capacity constraint, or you're incentivizing the market, or is the market static like that?
This one here?
The top bar is on the weekdays, I'm guessing.
It's capacity it's a combination of the way we run our business. So we try to get drivers home on the weekend, so that drives a lot of it. Companies that ship with us, their shipping operations tend to close on the weekend. So even though drivers may drive 7 days a week and take breaks in the middle and whatnot, it's just driven by the weekly cycle of business activity. Did that answer your question?
Exogenous is what you're saying. It's from the market, not more than your capacity.
Well, no, it's both. It's from the market, but our capacity is defined by what we want our drivers to do, which is we want to make them as happy as possible so they won't quit, as well as being as productive as possible for us. So that's so it's both. So the idea was, so I got all of these locations. If I'm trying to think about balancing my network and figuring about how do I make sense of trucks coming into an area and going back out of an area, and trying to manage matching up a driver just finishing a shipment with a driver taking a new shipment, what do I do? Well, we did some cluster analysis of freight locations. The engineering wasn't quite as sophisticated as I would have liked, but it was cluster analysis, I guess, thinking about several meanings of the word cluster. But we came up with, basically we had decided we're going to try to build this on zip 3, on a zip 3 basis with a couple of exceptions. So we have a few cases where we got a zip 3 and there are a couple of zip 5s that we glued onto it because they had a strong relationship. And then at a hierarchical level, we grouped that together again. We replaced a geography that was defined in about 1980. When I tried to figure out how it was defined, I was told that some individual that left the company in about 1981 came up with it and drew some lines on a map, and that became our geography. And over these years, as our business has changed and the network has changed, we were constrained by this. We were constrained by the fact that it was hard-coded into our old software. So one of the, I guess it was a little bit of clever accounting, but one of the huge benefits of investing in this new sophisticated ERP system was we changed our geography. And that was actually a significant component. So I looked at that same set of data based on these a little under 200 regions and about 30 areas. I just looked, I didn't take it day by day or anything, I just looked at, the net outflow and inflow at that level of hierarchy across the network. And you can see that, at least at an aggregate level, this geography pretty much keeps things, within a region or area, it keeps the balance reasonably good. And as you might expect, as I go to a higher level of aggregation, I drop the imbalance not quite half. This is what it looks like. So the black lines represent regions, the colored areas represent areas. So this is kind of how hierarchical works. So if a bunch of freight is coming in, and you can obviously see the more populated areas, the smaller the geographic footprint, but the idea is as freight comes in and out of one of these areas, there's somebody who's concerned. So there's a hierarchy of planners. There's a planner whose responsibility is to try to keep the southern half of California in hand. And then under that person, there are a number of planners who have responsibilities for the San Diego area and so forth. This is sort of the output of that cluster analysis, and you'll see an example on a slide later how we actually drive that inside the decision support engine. So just briefly, a couple of slides on the pricing side. So this is kind of the science that goes into this revenue management that I'm going to show you in a minute. And basically with contract pricing, so this is when things go out to bid and we try to analyze, you know, an opportunity from a potential customer and give them a price back which may be valid for 6 months or 18 months or up to 2 years. I think the example that Chris gave yesterday, there would be freight in there that we would commit a contract for 2 years. And the idea is, again, very simple. As we rate, so if our costs are fixed, the contribution or revenue that we're going to get per load is linear with the price that we're going to charge. So this is kind of a price per mile. But the volume that we expect to see from the customer certainly is the higher price we give back to them, our expectation for freight drops. And so there's obviously a lot more mathematics behind this. But effectively, if you put these two together, you get a very nice function where you can look at, based on my expected volume, this is kind of the sweet spot. This is as much as I can charge without going off the other side. And then usually this is fairly flat at the top, so you know we've got some room to play and people can adjust and use judgment. So that's kind of a one-slide picture of sort of the theory of how a truckload company would price in a bid setting. Spot pricing, a little more sophisticated. Again, I won't go into the details, but it's we basically, a logistic regression, so the output. So this is when I get a call from a customer and I'm going to quote a rate on the phone right now. And I want to give the person quoting the rate as much guidance as possible. So I've done some regression analysis, and I started with kind of a base price, whatever it was, the market price or whatever the mean is. And then through this analysis, I've kind of determined that there are some key factors that I should use to either reduce or increase that price based on the expectation that I have from the customer, or really the expectation that I want. So if I'm going to have 10 trucks, and I think I'm going to get 15 calls today for freight, I don't want to take the first 10. I don't want to make my price low enough that I'll take the first 10. I'd like to end up taking exactly 10 of them, and then I would back into the probability. I'd like the probability for each load to be about 2/3, because as the probability, if I can keep the probability a little lower, the corresponding price is higher. So you can see here are a couple of factors that we've teased out. A couple of interesting ones. If there's a trailer pull, if we have trailers at the origin or trailers at the destination, there's a much better chance that if there are orange trailers there, we're going to get some freight, because maybe they've already loaded the trailer and they've called and they're trying to negotiate a price with us. And you know, if there's a probability that if we can't reach an agreement, they're going to have to unload the trailer and load it somewhere, well, that gives us a little more to play with. So that's the pricing side of things. The cost side and I'll have to go through this a little bit quickly, but it's a standard kind of a linear programming model that uses dual variables. And the idea is, when I think about what it costs me to move a shipment, and here's two examples. I have one truck. I can go to LA or I can go to Miami. I make more money if I go to Los Angeles. I can charge a higher price. But and if I look at all my direct costs, Miami's cheaper because it's closer. But then if I think about what I have to do with that truck once it's in Miami, I need to figure out what's the marginal value, the shadow price, the dual. All of that concept encapsulates the opportunity associated with another unit of resource at that endpoint. And when you do the math there, you see, because in LA in this particular case, I've got a good chance of a load coming back east, but in Miami, unless I can fill that container with oranges the right time of the year, it's going to have to go empty back up to Jacksonville, and that may actually take a truck in Jacksonville and cause it to have to go empty up to Atlanta, and all of a sudden I got all these empty miles because I put another truck down in Miami. So this is just a pictorial of what this mathematical network flow model looks like. My profit is my revenue minus my cost, minus a dual value associated with a truck leaving a market, plus a dual associated with a truck coming into a market. And then I have arcs to represent the fact that a truck might have to go empty from someplace to someplace else to balance the network. Obviously, that's a bad idea. Holding a truck in the same place, it's not quite as bad, but not that good either. And this is what it all kind of boils down to. The user brings up a screen, enters the characteristics of the load, pushes a button, it goes off, and it comes back with an estimate of what we call the dynamic contribution, which is what I expect my margin to be. This particular load, take it on the 4th, I think I'll clear 1277, take it on the 5th, 1285, take it on the 6th, all the way down to 804. Because based on other freight that's in the network, on the 6th, I already think I'm going to have excess capacity in that market. So this is what the decision support, both the pricing component and the cost component, brings back to the user. So this is, and now I'll move kind of, so once we've done that, we've gotten orders, and I'm monitoring the process after with BI and dashboards. This is the kind of thing we see. So I've got, in this dashboard, it's got all kinds of options, so you can filter and select and drill down to individual customer service representatives, or look across a manager or a division, and I can look by both static contribution, which is kind of an average thing that we look at, as well as this dynamic one, both for spot pricing and for contract pricing. And then you can't read these, but these, in this particular case, this just happens to be geographic regions. So, and you can have, you know, charts or different graphs, or if somebody likes to see the numbers, they can have that. So, but this is what we use to figure out how well this whole process is working. And if we see areas that, you know, are lagging behind, then we can dig in, and the first thing to do is to try to understand whether it's the business process. If it appears to be systemic, then engineering gets involved again and says, well, maybe we need to go back and maybe we made some assumptions in that, because that linear programming model is very complicated. It's got many, many cost factors in it and adjustments and whatnot. In fact, for many years I've been worried by the fact that it's so mysterious that I can't understand it. So, how am I doing? Oh, okay. Well, I'm not going to be able to do my last one, but it's just another example of the same process. So, an analysis, a couple of decision support models. This one I want to jump down to this. A piece of this user interface, because it ties back to the first drawing and the first section I did. And then we've got some interesting dashboards here. So I apologize for rambling early and not leaving myself enough time, or being optimistic when I put together the presentation. So this is all available to download, and if you look through it and you have questions, send me a note. I'd be happy to have a phone call and explain to you what it means. This is what I wanted to get to. So back at that kind of designing that network and figuring out the regions. So those people that are kind of trying to balance the network from a broader perspective, at a regional perspective, somebody's looking at a map like this. The darker the blue, the more I need trucks to get into that area, because I've got more orders than I can handle, and then there's some specific numbers that can be positive or negative. And then below that, the next level down, this is most often somebody would be looking just at a piece of this, but this is the same thing down at the region level, where the darker the blue, kind of the more I need. It's also kind of overlaid with green, yellow, and red. Green means I'm in pretty good shape, or I've got too much. Yellow means I'm right where I want to be in the middle, and red means I'm short of trucks. And the reason these don't correspond very well is the dark blue is kind of what is happening, and these numbers represent how it's changed as I have gone ahead and made preliminary decisions to push freight out if it's got a wider time window, or move things in some other way. And then we've got some dashboards in the execution space. So a shift is when a truck has to move somewhere empty. So we've got some very detailed analysis of how many times we have to shift, how many miles we have to shift, where in the country we have to shift. And by division, so you can slice it any way you want, all from the same data model. This drills down to an individual manager of drivers, and you see how each one of these is a truck driver and how they're moving across the country, how many miles they've driven today. And I was going to show you some ad hoc queries, but that's just kind of a picture of. So not only do we have the dashboard environment, there's a robust environment for business users to go in and query all the same data on an ad hoc basis. Okay, with that I'll stop. Thank you.